Hey everyone, so we'll look at 104 maximum depth of binary tree. This is a good binary tree question, and let's see how many times it's been asked. Yeah, it's good amount of companies like to ask this question. LinkedIn like this question a lot, Amazon, then Spotify, Bloomberg. Cool. So yeah, let's see. Given the root of binary tree, return its maximum depth. A binary tree maximum depth is the number of nodes along the longest path from the root down to the farthest leaf node. Okay, so depth, by depth it means the height. So 1, 2, 3. So 3 is the height of this. So the better way of doing this, like my intuition is saying, use a breadth first search for this question, and then yeah, so because we can traverse the breadth, and as soon as and when we are traversing the breadth, we can count the number of the current level that we are on. So that would be the height. So yeah, we can finally reach the end and then return the maximum height of this. So let if we can say if root equal to null, then we'll return 0, which means there is nothing, return, or else we can say max or depth is equal to 0, and we'll simply return depth. Or let's say we don't even have to check this. What we'll do is we will take a queue, make a queue, and then put the root in that. Actually, we don't need to check, right? Because yeah, root equal to null, then we have to return depth. Yeah, because when we'll shift this root, at that point we are considering that it's the valid node, and at that point we end up increasing the depth, so we don't want that. So yeah, that edge case needs to be checked. So yeah, we'll go here, and as previously what we did was let size will give us the level, or let level is equal to, not level, let size of the current level, size, or let's say current level size is equal to yeah, this will give us q dot length, and okay, yeah, that this will give us current level size. And then what we can do is for let I is equal to 0, I is less than current level size, I plus plus. Okay, and as soon as we are done traversing the first level, we can just increment the depth and finally return depth. Okay, so what we need to do here is that shift the current element. Current is equal to q dot shift it, and then if current dot left is there, then we simply push it to the q current dot left, and if current dot right is there, then we push current dot right. Yeah, once we do this, yeah, we have to do this all the way till the depth is reached. Like we reached the leaf node, and then I guess this should work. Yes, so this worked. So again, the time complexity for this would be O of n, and O of n a setup. O of n would be time complexity and space complexity, as we are using a queue. So it will be again O of n, which is height of the tree. Okay, so can it be done recursively? I believe yes, it can be done recursively. So yeah, it can be done recursively, I believe. So this is pretty much clear, right? Yeah. So let's see if this can be done recursively. I did not time this up. So in streaming, I can see it's 6 minutes. So in less than 5 minutes, we were able to figure out the solution. So we're good here. So that was search we used, and then let's use DFS and DFS. And if suppose root equal to null is there, then we simply return 0 at that point. Okay, that is the base condition of ours. And then what we need to do is let left is equal to, we will find max depth of root dot left. Let right is equal to max depth of root dot right. So initially, once we go down the leaf here, it will return 0 and 0. So here we can mark it as 1. So the idea is we have to start counting from 1 and then send it to the top, and then so on and so forth. So whatever maximum that we get from both of the leaf, we have to send the maximum one. That's the idea. So let return max of left or right plus 1. So that's the idea behind this one. So math dot max. Let's get rid of this autocomplete, because in interviews we won't have autocomplete. So yeah, we're returning math dot max, left or right. So yeah, this is pretty small solution for this guy, but it works fine. So O of n for both of them. Cool. So last time I did this was in June 7, and now I'm doing it again. So yeah, good one. Now diameter I haven't done, so let's do that in the next stream. Hopefully the idea behind this. So let me draw a tree and then explain what we did in both of BFS and DFS. So I'll make the same tree here. 4, 2, 7, and I'll keep this tree as a small tree, and 9. And let's get rid of this guy. Delete. Then oh, oh, I don't know what will happen now. Okay, I guess I need to. Okay, 1, okay, 4, 2, 7, 6, 9. Intentionally, I've kept it like this so that I can show. Oh, where did it go? Okay, this app is behaving buggy. What to do, man? Okay, sorry guys. Okay, got this. So select this bad boy, delete this. Okay, cool. So I have this tree with me, and here what we'll do is, so PFS, the idea behind PFS is, this is level 1, this is level 2, level 3. So we traverse this guy and then update the depth to 1. Traverse this guy, update to level 1. Traverse this guy, update, sorry, plus 1 to the depth, so it will become 2, then plus 1, then 3, and then finally return this as result. Okay, so that's the basic idea behind it. So okay, and in DFS, what we do is we initially go to the left, like we traverse the left child until we find the null. As soon as we find null, we send it back and store it in left, like 0. As soon as we find null, we send back 0, we store it in left, and then we traverse the right, and then once we find null, we send 0, and we see which is the maximum of both of them, and add 1 to it and send back. So this guy will send 1. Okay, 1, and then we go to the so once the left side is done, we go to the right. We have to traverse this right, and then we go to 7. Then we have to go to the left. Then we go here. Then left is null. Return 0. This is null. Then traverse right. This is null. Return 0. Add 1 to this. Find the maximum of this between 0 and 0, and then add 1 and return. It will return 1. So once it gets left, go right. Then here we find another node, go to its left, it returns 0, go to its right, null, then return 0, find the maximum of both, add 1. So here also 1 comes. So find maximum of left and right, which is between 1 and 1, and add 1. This returns 2. So here it gets interesting. So here 1 is there and here 2 is there. So we find maximum of these two and then add 1. Then we return 3 finally. So that's the basic idea behind this. Okay guys, hopefully this explanation was understandable, and both of them is of n time complexity, and as we are storing the calls for each node, the space complexity is also of n. for both DFS and BFS. Okay, see you in the next